So quick again recap. So last time what we did mainly last time was actually to discuss an introduction to information theory and source coding. In particular, we have looked at the concept of entropy, right, as a limit on source coding performance, right? So we said that eventually any source coding technique cannot do better than the entropy. Better means less number of average bits per message. So the entropy gives you the average number of bits per message, and you cannot have a source encoder, which is lossless, that can perform better than that, which means that it can do less number of bits than the entropy. You cannot do that, okay? And then we have also discussed the case of fixed length source coding, right? And then we looked at the method for variable length source coding, which is basically the Huffman code. Last time we only described the method, but we never did an example on it. And I told you it will only become clearer as we do an example on that method. Because just looking at the steps does not make it clear enough to understand. So what we will do today is going to be, so today, the agenda for today are two things, two main things. Number one, we are going to take examples on source coding. Okay, so we're going to solve some numeric examples. We are going to discuss information theory for channel coding. We said that there are two branches for information theory. One deals with source coding. We have discussed what we need to discuss in that branch. We will discuss today the limits imposed on channel coding by the information theory and what do these limits mean. So that's another thing that we will do. And then one sub-item, we will have quick discussion for the course project. Right, I told you we will discuss this in the third week. The third week has passed, so let's do it now before we are too late to discuss that, right? And I'll post also all the material related to your course project tonight on your Blackboard. So let's start without delay, taking the example on, example on Huffman coding. Example. And the example says that assume that a source has 6 possible messages, okay, with probabilities. So the probability of each message to occur are given as 0.3, 0.25, 0.08, 0.1, 0.12, and 0.15. Okay, then you are required to design a Huffman code for this source. Okay, and then after that compare its performance, so the performance of that Huffman code to the source entropy. Okay. So let's start by the first part. Design a Huffman code for this source. So the first step in the Huffman code design was doing what? Sorting out the messages according to their probabilities in a descending order, right? So let's give the messages some names. Let's call them M1, M2, M3, M4, M5, and M6. We have 6 messages, right? The probability of the first one should be the highest, which is 0.3. The second should be the second highest, 0.25. The third should be 0.15. And then 0.12. And then 0.1. Last is 0.08, right? Then the next step is going to be aggregate the lowest 2 into one message, right? When you aggregate those 2 into one message, what's going to be the probability of that message? So 0.18, right? Now 0.18 would fall where? Above 0.15, right? So basically, you will end up with the new arrangement is going to be 0.3, 0.25, and then we get the 0.18 here, and then 0.15, and then last 0.12, right? So we have aggregated those 2 into one message. That message became with a probability of the sum, which is 0.18. So when we reorder, we end up with 0.3, 0.25, 0.18, 0.15, and then 0.12, right? Now next, you repeat the same thing again. So you go to the lowest 2, you aggregate them, right? And the result of that aggregate is going to be 0.27, sorry, 27. And that 27 is above 0.25, below 0.3. So the end result of the rearrangement is going to be 0.3, and then 0.27, and then 0.25, and last is 0.18. So basically, this one went up to this point, right? Okay. And then again, you keep on doing this. So we aggregate those 2. The result is going to be 0.43, which is actually the highest. So it will go at the top of the list, right? So the new list is going to be 0.43, and then 0.3, and then 0.27, right? And then anything else? That's it, right? So this one went up here, and that's the new column. Okay. Last, aggregate those 2, and the result of the aggregation is going to have a probability equal to 0.57. So that's basically going to go again on top of the list. So the top of the list here is going to be 0.57, and the next one in the list is going to be 0.43, and that's the end of the process. Because as soon as we reach only 2 probabilities, we stop there. Tamam? Okay. Now that's the first 3 steps, right? We said do the arrangement, combine the last 2, and rearrange. Repeat until you reach, repeat the combination of the last 2 until you reach 2 possibilities only, right? Now the next step is going to be going from the most right, okay? Start with this one, allocate 1 bit for this case. With higher probability takes a value 0 for the bit, lower probability takes a value 1 for the bit. So basically, what we will do is we go to the left, the rightmost, and then we allocate 1 bit. The bit is going to be 0 here. It's going to be 1 here. Okay? Now move 1 step backward. Okay? When you move to the left. So when you move to the left, anything that was not broken down just transfers the bits as they are. So basically, this guy is going to go here with the same bit. Right? Anything that breaks down, you transfer the bit again. So the 0 transfers to both of these. And then you add a new bit because of the breakdown. Okay? So the new bit, again, the same way. It's going to be 0 for the higher probability. It's going to be 1 for the lower probability of the broken down. So the new bit will have a value 0 here, 1 here. Okay? Move to the left. Whatever is not broken down transfers as is, right? So basically, the 0.3 goes here, the 0.27 goes here with the same bits, 0, 1, 0, 0. No change. Okay? Now the 0.43 went back and it was broken down. So first carry the bit to the broken down. So we carry that 1 value and then we add a new bit with the same logic. For the upper probability, it's a 0 value. For the lower, it is a 1 value. So 0 here, 1 here. Okay? Continue with the same exact procedure again. So this, no change, and it is 0, 0. 0.27 is broken down, leave it to the end. 0.25 is transferred as is, right? And 0.18 is transferred as is. So this is 1, 0, this is 1, 1, right? And then we go to the 0.27. It was 0, 1, transfers the 0, 1 as they are. So we have the 0, 1 here, 0, 1 also here. And then add a new bit. The upper value is going to have 0. The lower value is going to have 1 for the new bit. Yes?
Why didn't you add a new bit for the third column?
Fine, I didn't add a new bit.
0.25 and 0.18.
Yeah, I did. It was only 1 bit here. I transferred the bit and then I added 1 bit.
But it was already 2 bits in the second.
2 bits on these. These have nothing to do with this. Right? We said you add a new bit only for the one that's broken down. The one that was broken down was only 1 bit. And then when we go here, we add 1 more bit. Right? It's not add a new bit to every one. Otherwise, it will become fixed length. Right? Then again, we repeat the same operation. So the 0.3 goes back as it is. So it's a 0, 0. The 0.25 goes as it is. So it's a 1, 0. The 0.15 as it is. So it's a 0, 1, 0. The 0.12 as it is. So it will have a value 0, 1, 1. And then the only part which is broken down is the 0.18. So you carry the bits first, 1, 1 for both of them. So the 1, 1 appears for both of them. And then you add 1 more bit, and again, 0 for the upper probability, 1 for the lower probability. And you end up with your encoded messages as M1, M2, M3, M4, M5, M6 with the bit allocations 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, and then last 1, 1, 1. These are my Huffman encoded messages. So if I want to send M1, I'm going to send 0, 0. If I want to send M2, I'm going to send 1, 0, and so on. Okay? Now, how do we, first of all, any questions about the steps to do the Huffman encoding?
Can you repeat the step?
Sorry?
Can you repeat?
Repeat it. La, you watch the video. No, you watch the video. Repeat.
From the second level, not the...
Watch the video. Repeating the steps, watch the video. Any other questions other than repeating the steps? Yes?
The 0, does it matter like for M4011? So does the 0 matter, or I can just write simply 1?
You cannot cancel anything. It does matter. We are not really writing digital numbers. We are sending actual data with bit encoding. So it doesn't matter whether the 0 is on the left side or the right side. It doesn't matter. It still has a meaning. Yes?
We have 2 same probability.
You can keep them as they are. Keep them as they are. What do you mean same probability? You don't need to reorder if you mean for the ordering. And if you mean for bit allocation, if you keep them at the same order, you put the upper one with 0, the lower one with 1. Same thing, right? So you don't need to switch the logic. Okay, even if they are the same probability. Upper one is 0, lower one is 1. Okay? Any other questions?
M1 and M2, we have only 2 numbers. But
Yes.
starting from M3,
Yes.
so that means...
What's between?
Same.
Yeah, but that's called variable length encoding, right? So it means that not all the messages will have the same length. Otherwise, it would have been fixed length encoding, right? Okay, any other questions? Okay, so that's in terms of how you work out the Huffman source encoding. Okay, now the other question, the other part of the question says compare the performance of this Huffman encoding, okay, to the entropy of the source. So first of all, what's the entropy of the source in this case? What's the entropy of the source? How do you calculate the entropy? What was the equation for the entropy?
Log base 2 for m.
Which m?
Number of bits.
The entropy for the source. The source entropy is calculated as, is defined as? Yeah. Summation over all possible messages, pi, the probability of the message, log to the base 2, 1 over pi. And you sum over I, which is going to be from 1 up to 6 in this case. Okay? So basically this is equal to, first message has a probability equal to 0.3. So it's 0.3 times log 1 over 0.3 plus second message has a probability equal to 0.25. So it's 0.25 log to the base 2, 1 over 0.25 plus 0.15 log to the base 2, 1 over 0.15 plus 0.12 log to the base 2, 1 over 0.12 plus 0.1 log to the base 2, 1 over 0.1 plus 0.08 log to the base 2, 1 over 0.08. Okay, can anyone do the math and tell me what's going to be the result of this? Again, you can do it this way, and it's exactly similar to saying minus summation pi log to the base 2 pi, right? It's the same thing. Whether it's log 1 over pi or minus log pi, they are the same. Okay. What's the result? What's the entropy?
Why the sum probabilities should be equal 1?
Because these are all the possible messages that comes from the source. What else can happen? Right? Yeah. So, جماعة, 2 point. .4 2.4 what?
The first one is 0.156.
0 point? لا لا, this whole thing?
The entire thing?
Yeah. Approximately 2.42. I think it's 422, yes. Right? Yeah. Okay. So that's basically the entropy of this source. What does this mean? First of all, what's the units of this? Bits, exactly. And what does it mean? It means that the minimum number of average, the minimum average number of bits that you can use per message, the minimum average number of bits that you can use per message to encode this data coming, or these messages coming from the source, is equal to 2.422. This is an average value. That's why it's not an integer. It can be non-integer, right? It's an average value, average number of bits. So some messages, like what we see here in the Huffman, can be encoded with 2 bits, some encoded with 3 bits. When you take the average, it should be, if it is optimal, it should be equal to 2.422, the entropy of the source, okay? Now, that's the entropy of the source. What about what we have designed here, the Huffman encoded messages? What, in order to compare that with the entropy, what do you need to calculate? The average number of bits per message. How do you calculate that? That's the entropy, the first part. Second part is for Huffman. Okay, average number of bits per message is equal to, how do you calculate the average number of bits per message for this Huffman encoded source? يا جماعة
6 messages.
أيوة. Yes. So you take the number of bits here multiplied by the probability, plus the number of bits multiplied by the probability, plus the number of bits multiplied by the probability, and you add. This is how you get an average of anything. The average of x, the expected value of x, is equal to the value of x multiplied by its probability plus the other possible value of x multiplied by its probability, and so on, right? Here we are looking at the average number of bits. So we go for every message, we see what's the number of bits, we multiply it by the probability of that message, right? And then we add them together. This is going to give you the average number of bits per message, right? So it's equal to the summation of, let's call the number of bits for message I, okay, Ni, okay, multiplied by Pi, okay, and you sum over all possible values of I. What's N of I? Ni, by definition, is the number of bits for message Mi, for message number I. Okay, so M1, the number of bits in the first message, right? N2, the number of bits in the second message, and so on. So this is equal to, if you put the numbers now, 2 times 0.3 plus 2 times 0.25 plus 3 times 0.15 plus 3 times 0.12 plus 3 times 0.1 plus 3 times 0.08, and the total is going to be equal to 2 point. So this is 2.44. Okay. Now, is this greater than the entropy or smaller than the entropy? Greater. Can it be smaller than the entropy? No way. You cannot do that. Now, we said earlier that Huffman is optimal, right? You cannot do better than Huffman. But we can see that Huffman, even in this case, does not reach the entropy. This means that no matter what you use to encode this particular source, you are not going to do better than 2.44, even though the entropy of the source is 2.422, right? Because you cannot do better than Huffman. So the note here is going to be that despite Huffman coding being optimal, okay, in some cases, even Huffman cannot reach the source entropy. Okay? So even though you cannot do better than Huffman coding, but in some cases, even Huffman coding, which is the best that you can do, cannot reach the source entropy. Okay? Now, in general, Huffman is going to reach the source entropy. It can reach entropy if number of messages is integer power of 2. So for example, if this source had 8 messages and you use the Huffman method, you would have found that the Huffman is giving you exactly the entropy. Or if it was 16 messages, so these are 2 to the power some integer, right? So 8, 16, 32, and so on. But if it is 10, if it is 15, if it's 20, in those cases, you might not be able to reach the entropy of the source. خلاص يا جماعة؟ Okay. Now, there are two important properties of Huffman. Okay. The first one is, it is optimal. You can't do better. Okay. So regardless of what coding method you use for source coding, you cannot do, for lossless source coding, you cannot do better than Huffman. So that's the first property, and we mentioned it already since last time. The second one is that it is instantaneous. Instantaneous. Okay. It is instantaneous, which means that no code word is a prefix of another one. What does this mean? Look at the messages that we have just encoded in the previous example. So M1 was equal to 0, 0, right? M2 was equal to, who has the list? 0, 1 or 1, 0? 1, 0. M3 was 0, 1, 0. M4? 0, 1, 1? 0, 1, 1. M5? 1, 1, 0. M6? All ones. Okay. Notice that. Okay. If you look at M1, 0, 0. Okay. You can never find another code that starts from the left with 0, 0. Can you find anyone that has the leftmost 2 bits equal to 0, 0? No. The same for 1, 0. Right? For M2. Go for M3, there is no 1, 0 to the left side. M4, there is no 1, 0 to the left side. No 1, 0. No 1, 0. And so on. Okay? And if we had more code words, so that we use 4 or 5 or 6, you will also notice that these, the M3, M4, and M5, and M6, which are 3 bits, you will never find them as a prefix, as a starting part of the coming codes that are of 4 or 5 or 6 bits long, and so on. Right? Why this is desired? Why this is good? Because it allows you to decode the shorter ones instantaneously. That's why we call this an instantaneous code. So imagine that you are a receiver and you are getting bits, right? As soon as you get 0, 0, you will immediately know that this is M1, because 0, 0 will not appear at the start of any other code word, right? So as soon as you get 0, 0, immediately, you don't have to wait for the next bit. You can immediately say M1 decoded, and you generate M1, right? As soon as you get 1, 0, you will generate M2. You don't have to wait for the next bit. Similarly, imagine that we have more with 4 and 5 and 6 lengths. As soon as you get 0, 1, 0, you will immediately decode M3. As soon as you get 0, 1, 1, so 3 bits only, you will decode M4, and so on, right? So you don't have to wait for the maximum length to be able to decode. You can just decode as soon as you reach the minimum length requirement, right? Okay, that's called instantaneous decoding. That allows you to save on delay at the receiver in terms of decoding the messages. خلاص يا جماعة? So in order to be instantaneous, in order for any code to be instantaneously decodable, the property is that no code word is a prefix of another one. You cannot find any code word at the start, and the start here we look from the left side, at the start of any other code word. Okay? That's called instantaneously decodable code word. Okay? Now.
When the receiver receives 5 bits, for example, how does he know that the first 2 bits, how does he know that the first message is only 2 bits, not 3 bits?
Well, it doesn't need to wait for that. As soon as it sees 0, 0, then this must be the first, because 0, 0 does not appear anywhere else. Right? Imagine that, for example, I receive this 0, 0, 1, 1, 0. Okay? I receive 5 bits. Okay? I receive this one first at time t1, and then I receive this one at time t2. At this point, at time t2, I know that it must be that those 2 is this one, because there is no other option. They cannot be in any other code word, right? Don't forget that our initial agreement is the source and the destination have a common dictionary. So I cannot send the destination something that he's not aware of ahead of time. I cannot send him British or English while he's expecting to receive Indian from me or Arabic, right? Because in that case, it will not be able to decode. So we have to have a common dictionary. So originally, the source encoder knows the messages, the possible messages, right, and their code, and the source decoder on the other side knows that the possible messages are M1, M2, M3, M4, M6, and these are the codes for those ones. Now the job of the receiver is only receiving a set of bits, figuring out which one was transmitted, right? But it cannot figure out something totally unknown. Okay? So if I receive this sequence, as soon as I receive 0, 0, I will know immediately that M1 has been there, and then I will start decoding a new word, right? Now new word 1, 1, 1 does not tell me anything yet. 1, 1 does not tell me anything yet. 1, 1, 0, oh, it must be M5. Done. Okay? So, and so on. Imagine there are more bits, the same thing will continue. خلاص? Any other questions? Okay. One more thing remaining. Let's compare, just for the previous example. Okay. Let's consider a fixed length source code. Okay, and number 1, find the code. Number 2, compare its performance to Huffman. Okay, so let's do the first one. Find the code for a fixed length source encoding. What do? I don't care about probabilities, right? First of all, I need to figure out how many bits to use, right? So I don't care about probabilities, I only care about how many messages I have, right? So the number of bits per message, 4. So 4 a fixed length encoder. Okay. Number of bits, n per message. This is the number of bits for any message, right, is equal to the ceiling of log to the base 2, right, the number of messages. What's the number of messages in this case? 6, right? So this is going to be equal to the ceiling of, what's log 6 to the base 2? 2.5. Doesn't matter the rest. Okay, so the ceiling of that is going to be equal to 3. So I know that each message has to be presented by 3 bits. What are the values of the 3 bits? It's up to you to choose under one condition, that they all have to be unique. You cannot represent 2 different messages with the same bit values, okay? So one can choose, for example, you have many choices in this case. You can say M1 is equal to 0, 0, 0, for example. M2 is equal to 0, 0, 1. M3 is equal to 0, 1, 0. M4 is equal to 0, 1, 1. M5 is equal to 1, 0, 0. M6 is equal to 1, 0, 1. That's it. These are the codes. You can choose something else. Someone might say M1 is equal to 1, 1, 1. M2 is equal to 1, 0, 1. M3 is equal to 0, 1, 1, and so on. The important thing is you cannot repeat the same bit pattern for two different messages. They have to be unique, okay? So the only important thing is they have to be unique, okay?
Well, the M3 and the M4 starts with 0, 1.
Sorry?
M3 and M4, they starts with 0, 1.
So what?
But you said it has to be unique.
Unique. Each code unique. I didn't say anything about prefix here, right? I said that each code word, like every 3 bits, have to be unique, which means I cannot use 0, 0, 0 here and use 0, 0, 0 here again, right? Prefix is a property that's important for variable length, right? Here it's fixed length. So at the receiver, every 3 bits, I'm gonna decode them because it's not variable length, right? It's fixed length. So I have no need for instantaneous decoding. Already I know that I'm using fixed length. So every 3 bits, take them and see what they belong to. Every 3 bits, look at what they belong to, right? I don't need prefix property here. I need the prefix property for the case of variable length. Some of the code words are 2 bits, some are 3, some might be 4, some might be 5, and so on. Tamam? So we don't care about prefix here. Don't mix the two things. Unique is something, prefix is another property. Okay? Now, this is the first part. Find the code. And there are multiple solutions for this. Someone might end up with this. Someone might allocate the bits in a different way. I mean, the values of the bits in a different way. Doesn't matter as long as they are all unique. No repeated pattern across them. So you cannot have 0, 1, 0, for example, used for 2 messages. You can't do that. Each message has to have its unique 3 bits. خلاص? Okay? That's the first part. The second part is compare the performance to the Huffman. What's the average number of bits in the case of fixed length?
3.
3, right? So here the average,
More bits.
exactly, number of bits per message is equal to 3, which is greater than the Huffman, which was greater than h of m, right? So we know that this fixed length encoding is doing worse than the Huffman, and definitely it's also worse than the entropy of the source. خلاص يا جماعة? Clear? So now we have looked at 2 things. Okay, we have looked at how we do encoding, whether it's using Huffman or fixed length. We have also looked at how you can calculate the performance of a particular source encoder. Imagine that in some case, I can give you a source encoder that you have never seen before. It's not Huffman, it's not anything else. I'll just tell you the XYMNO source encoder is allocating the following bits to the different messages. And I give you the bits for each message. And then I tell you, calculate the performance of this as compared to the entropy of the source. You don't care about how the encoding happened. What you care about, I have the bits for each message. Let me calculate the average number of bits per message, right? So each one multiplied by the probability and add them together, and then see how does this compare to the entropy, right? So don't get confused if you are asked to evaluate an encoder that you have never seen before. It doesn't matter. What you care about is what's the output of this encoder, and from that output, you can calculate the average number of bits, and then you use that to compare with the entropy. تمام؟ خلاص يا شباب؟ Okay. Okay, information theory. So the second part is information theory for channel coding. Okay. And there are two parts similar to what we did in the source coding situation. So remember, in the source coding, we ended up discussing two things. Number one, we discussed limits or boundaries, right? So limits / boundaries. Okay. On performance. And in the source coding situation, this was basically the entropy. When we discussed the entropy of the source, we found that this is a limit on performance of any source coding technique. Similarly, for the channel coding situation, we will see how we limit the performance, or how we can find theoretical limits on the performance of channel coding. And then the second part is again similar to what we did in the case of source coding. We looked at two different approaches to design source codes, right? The fixed length encoding and the variable length using Huffman code. There are many other ways, but we did not discuss all of them. We only gave you a couple of examples. Now, when you study further into digital communication systems, you can actually study some of the other techniques, right? But we only cared about showing you an example. Similarly here, we will see examples of design of channel codes or coding methods. Okay, so how can you, when you have a particular set of data, how can you design a channel coder and decoder for that set of data such that you increase, you remember what was the objective for channel coding? Increasing reliability. Source coding was more towards efficiency, channel coding was more towards reliability. Okay? Now again, just a reminder, performance, okay, measure for channel coding, okay, was mainly reliability, right? Okay, and reliability is measured in digital communication systems using bit error rate, or it's called also probability of error, which is typically given the symbol PE. So mainly the reliability in a digital communication system is measured by a performance parameter called the bit error rate, or the probability of bit error, probability of error, and it's typically given the big capital P and then E small beside it. That's a symbol for probability of error. Okay? Yes?
But we use parity, I remember last time.
Parity.
Parity to check the...
Yeah, parity was one example of how you can design an extra piece, add redundancy, right, to increase the probability of detecting errors, right? But that was not the performance measure. I'm saying what we use to measure the performance, not to do the channel coding. To measure the performance of channel coding is the bit error rate. In general, to measure the performance of digital communication systems, we use the bit error rate, okay? Which is the probability of encountering errors as you communicate. You can simplify this in case of doing numeric evaluation, that you send, for example, 1,000 bits from the transmitter, and then you see at the receiver how many you receive correctly and how many are in error. Let's say out of 1,000, you receive 2 in error, then the probability of error in that case is 2 over 1,000. Right? Every 1,000 bits, there is a probability that 2 of them are going to be in error. Okay? That's called the bit error rate, or the probability of error, as a measure of the performance of a communication system. Okay? Now we cannot measure the probability of error just in the absolute. We always measure the probability of error under certain transmission rate, R. So we always say that for a particular transmission rate, let's say for a transmission of 10 megabits per second, I want to achieve a probability of error that's 10 to the minus 5, for example. I want a probability of error that does not increase above 10 to the minus 5 for a particular transmission rate. It's not just in general. Why? Because those two quantities are tied together. If you increase the transmission rate, you typically increase the probability of error. Okay? So those two quantities, the probability of error and the rate of transmission, so PE, okay, and R, the rate of transmission, are tightly coupled. And your objective is typically to reduce PE, to reduce the probability of error, and increase the rate of transmission. That's the objective of any designer of a communication system, is to be able to send as much rate as I can, send a lot of data in very short time, right? And also without any errors if I can. So the probability of error should go to approximately 0, right? But those two objectives of increasing the rate and decreasing the probability of error are contradicting objectives. So typically, you have to trade off between them. Okay? You have to sacrifice one to gain the other and vice versa. Then how do you do that? It depends on what are the requirements of your communication system. Some communication systems, the rate is more essential. So basically, you have to achieve a certain minimum rate. You cannot be lower than that. And then for that minimum rate, you can look for what's the lowest error that you can do. Okay? In some others, the quality of the data or the reliability of the data is more important. So in that case, you set your target probability of error, and then you want to achieve as high rate as you can for this target probability of error. Okay? But you cannot really make both of them go to the optimal value. You cannot increase the rate all the way to infinity and decrease the probability of error all the way to 0. There is always going to be some error probability. It's not going to be equal to 0 because all our channels are at least noisy, right? So there is always going to be some error in the transmission, and there is always going to be some limit on the rate that you can send over the channel, right? So you cannot really take them to the optimal values both at the same time. خلاص يا شباب? So they are contradicting objectives, and typically you need to trade off. So when you perform trade-off, it means that you have to sacrifice one for the gain of the other and vice versa. Okay, so you need to strike some balance between those two quantities, but you cannot achieve the good of both of them at the same time. Okay. Now, given that this is the situation, okay, and given also one important thing, remember that okay, for a particular rate, okay, for a particular transmission rate R, you need a channel bandwidth of at least, right, R hertz, right? So this is bits per second, and this is hertz. So to transmit a certain number of bits per second directly to the channel, you need at least a channel bandwidth equal to the same rate. So to transmit 10 megabits per second, you need at least a channel bandwidth 10 megahertz, right? If your channel bandwidth is smaller than that, you cannot achieve the 10 megabits per second. Again, you can achieve that by converting bits into symbols, but it becomes the same thing. When we talk about rate, in that case, it's going to be symbols per second. So we are talking about the rate that goes into the channel, not the rate in some intermediate stages of the system. So if that, in that case, when you use digital modulation, what's going to enter the channel is going to be symbols per second, and the channel has to support at least a bandwidth equal to the number of symbols per second, right? So again, if you remember the block diagram, right? In order for a certain bits per second or symbols per second to go into a channel and exit from the channel reliably, Okay, the channel bandwidth, so that's R, whether it's bits per second or symbols per second. The channel bandwidth, let's call it W. It must be that R is less than or equal to W. If you try to put data into a channel and the rate of that data is greater than the channel bandwidth, what will happen? Some of the data will be lost because the channel is not going to be able to pass all the frequencies. So some of the frequencies are going to be cut off from your data, and cutting off some of the frequencies means cutting off some of the information. So this means that your communication is no longer reliable because you have lost some information as you go through the channel, right? Okay. So in order for reliable communication, okay, we need R, the rate that you put into the channel, has to be smaller than or equal to the bandwidth of the channel. Okay, so this is a channel. Okay, so remembering this, okay, and this is for ideal channel, right? So basically no noise, no filtering effect, or what did we call it last time? No gain effect, filtering, multiplicative, convolution, so no distortion, right? We called it distortion last time. Right? So in case of no noise, no distortion, so the channel is ideal. The only limitation is that it has a certain bandwidth. You have to make sure that the rate that you put into the channel must be smaller than or equal to the bandwidth of the channel. Otherwise, you will lose data, right? Now, what if, or rather than saying what if, for the case of noisy channel. So we will not consider the case of distortion in this course because it's quite advanced, so it requires you to take a second course in communication, but we will only focus on the case of noisy channel. Okay? What if we look at the case of noisy channel? What's going to be the limitation of my transmission rate? Okay? For the case of noisy channel, there is something called the Shannon capacity theorem. Okay? And what this theorem says is that you can achieve reliable communication, okay, over a noisy channel, okay, as long as the transmission rate R is less than the channel capacity C, where C, the channel capacity, is equal to W, the bandwidth of the channel, multiplied by log to the base 2, 1 plus SNR. And I will describe in a minute what's SNR. Okay? So this is what Shannon's channel capacity theorem says. If you transmit over a channel which has some noise, okay, with a rate R, which is smaller than the channel capacity is a property of the channel itself. Okay? So if you transmit with a rate smaller than the capacity, then somehow you can achieve reliable communication. Reliable communication means that you can do something such that the bit error rate tends to go to 0. So it becomes very, very, very small, approximately 0. The theorem here tells you that you can do this, but it does not tell you how to do it. Okay? It just puts a limit. It says that if the opposite, think of the opposite. If you try to transmit with a rate R greater than the capacity of the channel, forget it. No matter what you do, your communication is not going to be reliable, which means that your probability of error is going to grow and is going to become totally unreliable communication. خلاص يا جماعة? So again, similar to the case of non-noisy, if you try to transmit at a rate greater than the bandwidth of the channel, again, your bit error rate is going to grow and your communication will become unreliable. Similarly, for a noisy channel, if you try to transmit with a rate R greater than the capacity of the channel, you cannot achieve reliable. Some of the information is going to be lost. You cannot achieve reliable communication. خلاص? And what's the value of the channel capacity is equal to the bandwidth of the channel multiplied by the logarithm to the base 2, 1 plus the signal to noise ratio. SNR is, okay, SNR is basically signal to noise ratio. And it's defined as power of signal divided by power of noise. Okay, so if I know the amount of power that I send the signal with, the average power that I send my signal with, and I know the average noise power at the receiver side, I can calculate the SNR, and if I can calculate the SNR and I know the channel bandwidth, I can calculate the capacity of the channel. Now this equation adds one more parameter to the things that you trade off over the channel, right? Remember, we said that you trade off probability of error with bandwidth or rate, right? Also, you can trade off probability of error with power, right? Or rate with power, right? So there are three parameters. So in general, based on Shannon's theorem, we can see that in any digital communication system, we can trade off three parameters. What are they? Probability of error, okay, and we want this one to go as small as possible. The second thing is transmission rate. We want this one to go as high as possible. And the third one is power of signal. And what's the objective? You want to transmit with the minimum possible power or with the maximum possible power? Minimum. So you want basically to reduce this as much as possible. And again, those three objectives are contradicting with each other. So when you play with one of them, it just affects the other two in an undesired way. So if you focus on power and you want to reduce it, you will find that the rate is going to be reduced and the probability of error is going to increase. If you focus on probability of error and you want to reduce it, you will find that the rate is going to decrease and the power is going to increase, and so on, right? And again, which one to choose and how to trade them off is based on what are the required features in your communication application. You are using this communication for highly reliable things, for example, transmitting images of medical use. So in that case, probability of error is a big factor because you don't want to commit any error. Otherwise, it's going to cause wrong diagnosis, right? Someone is going to be diagnosed and treated according to these images, right? So these medical images have to be highly reliably communicated. So in that case, it's okay. I will spend a little bit more power. I will, for example, like give away a little bit of the transmission rate such that I guarantee that they arrive there with very high reliability because that's more important, and so on, okay? So again, the three are traded off, okay, because they are contradicting objectives.